Good morning, everyone. Let us continue in our lecture series on physical chemistry for electronic structure. We have covered the introduction. We have covered theorems and postulates. We have covered the variational method. And the perturbation method. Right now we're in chapter 5 on molecular quantum mechanics. And we've already discussed the electron density as well as dipole moment and polarizability. We started last week with the Virial Theory. And after a brief introduction, let me just recapitulate the fundamental findings. First of all, there was the Hypervirus Theorem, which states that your commutator, expectation value of your commutator of your Hamiltonian and some linear time-independent operator A, this expectation value must be 0. We then saw that if you use as A the sum over position and momentum products, that you then arrive at what is known as the Virial Theorem. Where 2 times the kinetic energy is the expectation value of the sum over your QI times the derivatives of your potential with respect to QI. Now this is very interesting and already a helpful finding. And this is known as the Virial Theory. Now, under certain conditions, this becomes extremely useful, namely if the function V is a homogeneous function. So if that's the case, a homogeneous function of nth degree, and if that is the case, you can equate the sum over the derivatives multiplied with a variable by the degree times the original function. Okay, and this is Euless theory. So we discussed this and we exemplified it. And if you substitute this, the Virial theorem becomes 2 times 2, the kinetic energy must be n times v. All right. So this is the Virial theorem for homogeneous potentials. As always, if there's something unclear or you have some questions, please don't hesitate to interrupt me or to write your question in the chat. If not, I presume that this is all clear. So here we have a relationship between the kinetic and the potential energy, and that is extremely helpful. And together with the relationship that your total energy must be the sum of the two, you can you can eliminate either if the other is known. So we had these formulas here. All right. Now we discussed some examples towards the end. In particular, we did discuss the harmonic oscillator and then the hydrogen atom. Now, for the quantum harmonic oscillator, we found that n must be equals 2, while for the hydrogen atom, due to the 1 over r behavior of the potential, we saw that our n is going to be -1. So that's a general thing. This 1 over r behavior leads to n equals -1. And from that, we see that t, 2t should be minus the potential energy. So we discussed the hydrogen atom, and I'd like to give now as a third example the all electron atom. Okay. So that is any nuclear charge. And it's for the neutral case, right? So for any, we're talking about neutral systems here. So this also neglects any spin-orbit coupling. So any electrons and neglecting spin orbit coupling. So in this case, your potential is minus C, sum over your electrons, 1 over distance to your atom, right? So that's the attraction to the nucleus. And then you also have the electron-electron repulsion in your operator, minus RJ. So if you look at this expression, you can now imagine again putting your S variable in front of X and Y and Z. So let's just illustrate this here. So you could have something like 1 over Sxi minus xjs squared plus Syi minus Syj squared plus Sci minus Scj squared, and all of that. Right. For this term, we already saw this in the hydrogen atom. You have n equals minus 1, or another s to the minus 1 here. And now if you consider the right, this term, you see that you have the same prefix s to the minus 1. So also for the all electron atom, you have the same Virial theorem as for the hydrogen atom. So this is also a homogeneous potential. Of degree n equals minus 1. And hence this picture that you can draw of the energy in terms of E tot, right, where you would have 0 and then 1. And this is E tot. And then you have 2. This would be V. And here you have minus 1. This would be kinetic energy. Right? So with this homogeneous potential, your V is equals 2 E tot, and your kinetic energy is minus E tot. All right, are there any questions? If that's not the case, we'd like to proceed now to the next subchapter, which is about molecules. What we will do now is to discuss the chemical bond in terms of this Virial theorem, and we will see we can gain an understanding of how kinetic and potential energy add up such that you obtain chemical bonding. So this third subsection on the Varia Theory, which seemed to be a little bit remote from any chemical applications, should now really start to shine and help you to develop a better quantum mechanics-based intuition and a better grasp on what chemical bonding really is. Right? It is important to note that there's no operator for chemical bonding. Right? The expectation value called chemical bond does not exist. Okay, as such, it's a concept, right? It's something we try to use to explain the resulting energetics, which drives things. Right, so it's a proxy for the energetics, right? And that's okay. There's nothing against using proxies, but you have to be aware that this is not a real observable, not an actual observable. Okay. So this is now our Chapter 5, Subchapter 4, Chemical Bonding. So you can start with the Born-Oppenheimer approximation. Which tells us that our full wave function is, roughly speaking, a product of the electronic times the nuclear wave function. Okay. Now we're gonna use again our variables Q for location, and that means that we have here for psi and really a function of the positions, the positional vectors of some nuclei. And we'd like to denote this with the Greek letter alpha, which is also, sometimes one uses capitalized indices, sometimes one uses Greek letters to indicate that we are talking about the nuclei. Right? Some people also call them ions. Right? These are the ions, meaning that comes from this idea of a bare proton. Right? So the hydrogen, the cationic hydrogen ion is just a bare proton. So nuclei or ions or atomic positions have Greek letters. The electronic wave function depends on, of course, your electronic coordinates, and also parametrically on your nuclear coordinates. Okay. So in there you have both, and that comes, just think of the external potential interacting with your nuclei, right? That imposes this atomic dependency, atomic position dependency. Now we solve the electronic problem for any given geometry. This is also known as a single point. We solve the electronic Schrodinger equation. Right. So that is standard. This is Euless, and let me call this tot. Right? So this contains your. I'm sorry, this is not done. It's just the electronic part. That means, clarify this further. This Hamiltonian here contains the kinetic part and an electronic part. Sorry, a potential part. Both are electronic. And this potential part is commonly split further into a potential electron-electron interaction term and a potential electron-nuclei interaction term. Okay. Now, what is E tot? E tot is Euless plus E nuclear repulsion. Okay. So the nuclear repulsion is not something we need to deal with in solving the Schrodinger equation. You can include it in the operator. It's all classical. The electronic contribution collapses just into its own inner product, and so you don't need this term to solve the electronic Schrodinger equation. All right, so the question now is what can we do about these operators, and in particular, what about this potential term? Is it homogeneous? Okay, so we can we know the kinetic operator. All right, let's get rid of this one. This you know, but the question now is our potential homogeneous? Right? And this is something we discussed already. So we can look at these terms again. So you have these two guys are the same as minus, sorry, the repulsion. All right, and here we have the terms I write them explicitly for every component, so that our discussion of the degree of the homogeneous function becomes easy. right? So having the atomic discussion before in mind, right? This first electronic repulsion operator, that's the same, right? So this is homogeneous degree n equals -1. Right? And now we have the electronuclear attraction, so a negative sign, and I sum over all my atoms now. Before I had just one atom, right? But now I have to sum over alpha too. Now what happens here? If you see alpha, and now you divide by xi minus x alpha plus yi minus y alpha plus ci minus c alpha. All right. So that's our denominator. But can we now use our Varia theorem here, right? So if you look at this, you will notice you have a problem, right? So if you take 1 over s qi minus q alpha, right, this is not the same as s to the minus 1 over qi minus q alpha. So you cannot factor out your s like that if it's just in front of your qi and not in front of your q alpha. All right. So in other words, as long as you consider solely the electrons, your VEN is not homogeneous. Okay, so that's annoying. So we didn't encounter this problem in the all-electron atom because there was only one nucleus, and so you could basically cheat and put the origin of your reference system onto this nucleus, and then you would only have the electron distance to that origin, right? And then it still works. But if you have multiple nuclei, you cannot factor it out like this. So is there something we can do nevertheless? And it's actually quite obvious. It's basically we restrict ourselves that we cannot really separate the electrons from the nuclei for this, but rather that we have to have something like a joint Virial theory, where we treat electrons and nuclei on the same footing. Okay, so because of this, we should apply Virial theorem to electrons and nuclei. Right? Now, that's not a crazy idea. Just remember what we did above to arrive at the Born-Oppenheimer approximation. We approximated this, right? We did this approximation here. But we do know very well that nuclei and electrons are part of the same many-body problem, right? And they are part of the same wave function. And so just because we make this approximation doesn't mean that we should forget everything where it's coming from. And so this idea to sort of reunite again nuclear degrees of freedom together with the electronic degrees of freedom is not something surprising or outrageous or whatever, right? It's quite plausible. So this is then super easy, right? So if you're allowed to use 1 SQI minus SQ alpha, right, then of course n equals -1. Now, what does this mean? This means then that our virial theory should really be sum over I QI dQI V plus the nuclei Q alpha dQ alpha V, right? In some sense, there's some, I just split it out, right? But you're summing over all your particles, no matter if they're electrons or nuclei. So this thing must be equals our V minus V Eule. Now, we like to rearrange things a little bit. In particular, you can simply shift this to the other side, and then you have QI dQI V minus V Eule plus alpha Q alpha dQ alpha V. You'll see in a minute why, but what is really the tricky and annoying part, right, which we wanted to get rid of, is what's here on the left-hand side, right? That's the tricky part. And we don't know a priori the shape of the potential with respect to the derivative of the potential with respect to electronic degree of freedom. But actually, the derivative with respect to nuclear degree of freedom, that's something a little bit easier, okay? Because strictly speaking, that's not part of the electronic problem, because of the following, right? So let's write this out. The whole thing here, right, has to be equals 2t, right? So this is 2 times psi Eule t psi Eule, right? Just written out. And now I can, that's what this is, right? So I can write this to be the same as the expectation value V Eule. And now I have to take the expectation value of my of the sum up here. Now, what you see is that you sum over the nuclei, right? And the nuclei are just parametric. So you can pull your nuclei out, and also their positions are parametric. And so you're left with psi Eule dQ alpha V psi Eule, right? Now, this here is the derivative of your Hamiltonian with respect to an external coordinate. And that's something we discussed already. That's the Hellman, you can use the Hellman-Feynman theorem, right? And so this is nothing else than dQ alpha E Eule, right? By virtue of the Hellman-Feynman theory. So in other words, that's just the force, right? That's the force on your atom. So what you really have here is 2 times T equals V at the L minus you sum over your atoms, their coordinates times the force. Okay. So this is the electronic force. It's not yet the nuclear. I notice there's some chat. Let me. Okay. So yes, so we see that we get some very compact expression again, and basically with respect to what you're used to is you have to extend, you have to add this force term, okay, and this is known as the molecular Virial Theorem, okay, and in particular what you find here obviously is that if your forces here are 0, right, then the conventional Virial theorem for homogeneous potentials applies. But so that for your forces to be 0, that requires you to also then ask what happens to the nuclear repulsion force, right? So we should ask this question now: which role the nuclear repulsion plays, right? As you see here in this box, we are talking only about Euless right now, right? So this force here is just our dq Euless. So what about this nuclear repulsion? It turns out it actually it doesn't matter, because it actually cancels, and let us see why. So your total potential, right, is your Euless plus your nuclear repulsion term, and this nuclear repulsion term, you know, is the double sum where alpha is larger than beta to avoid overcounting. And then you have the distance in the denominator. And these are vectorial properties. I should also actually note the vector. And now we plug that in the total Schrodinger equation. So the total and this gives you the total energy, and above I denoted this as E tot. Let's call this is the same as U, okay? Just another common symbol for the energy. So we call this U, and U depends only on your nuclear coordinates, because through calculating our eigenvalues and our expectation values, we integrate out the electronic degrees of freedom. Okay. So this U must be equals the E Eule in parametric in your coordinates plus your nuclear repulsion, right? And this is our potential energy hypersurface, right? Now we can use this in our Virial theorem. And then we must have the Eule and the nuclear part, yeah? I mean, this is the dot, okay? Yeah, so if you just look at this, right, it's clear n equals -1, right? It's also homogeneous. So for this reason, we can write it like this, and so we also have still from the Eule, right? So from up here, the Eule is not only that, but also this sum over Q alpha dQ alpha, and now we have to use it for the U because it's for everybody. And so what you see now is that you get here really the potential energy of Nn, and if you write this out, you have the sum over alpha Q alpha dQ alpha E Eule. That's our force, our electronic force, and then you also have the sum Q alpha dQ alpha VNN. And now, because VNN is a homogeneous function, right? This is equals this bracket here is equals minus VNN. Right? This thanks to Euless theory. So you have this VNN, and this is your VNN, right? And so these two terms exactly cancel, right? This one and this one, they cancel. And so you see that the nuclear contribution to the force in the molecular Virial theory drops out. Right. So, in short, U2 T Ele minus V Ele minus sum over Q alpha dQ alpha E Ele. And this is the same if you add VNN and you subtract VNN at the same time. It's the same as V dot minus sum over Q alpha D Q alpha U. Okay. Now, this is this version is maybe the second version is more intuitive, right? Because this is really the potential energy surface, this U, right? So this is the most intuitive way, right? And it tells you that when forces on atoms are 0, right, then you're either in a minimum or on a saddle point or in a dissociated regime. Under any of these circumstances, you recover the same expression as for the atom. So in the equilibrium, or in the stationary case, in all stationary cases. So in particular, if you have some binding curve, right? In this case, you know your 2 times your kinetic energy must be equals minus the total potential energy. Okay, we will discuss this in more detail after the break. It's 11:02 now, so let's have a break until 11:18, please. All right, let us continue with the course. We arrived at the Virial Theory for molecules, okay, multiple atoms, and we saw that it's not as easy as for individual atoms, but with this simple extension of containing this force term, you have a really helpful relationship. And now we'd like to use and demonstrate the usefulness of this. And we want to do this for the most archetypical kind of scenario of a chemical bond, which is the diatomic. Right? And now we are talking any diatomic. Right? This can be hydrogen fluoride, this can be N2, this can be CO, this can be iron chloride, whatever. Doesn't matter. Okay, so it's the immense universality which we inherit by the virtue of quantum mechanics, and which we now exploit to look at truly any diatomic. Okay, so this is the case of the diatomic. Now, just to further stress the fundamental importance of this, to a rough order, you can think of any molecule as a sum of diatomics, right? Summing up these diatomics gives you the molecular graph, right? So if you like to think of molecules, and it would be 100% consistent now with the idea of simply summing up the diatomic discussion as we do it now, okay. As we discuss it now. All right. So for the diatomic, the first thing we'd like to do is to switch to the internal degree of freedom, the internal coordinates, right? So we would like to facilitate discussion. We would like to project our degrees of freedom onto the interatomic distance. So we'd like to project our Q's, right? Our degrees of freedom onto interatomic distance R. Okay, so let's write this. This is fairly straightforward. So assume 1 degree of freedom. Let's say the X component of atom alpha, and your electronic energy. This force component, we simply make use of the chain rule. Okay, so this is an old trick. We first derive the energy with respect to R, and then we derive R with respect to the component. Okay, now what is R? R is X alpha minus X beta squared plus Y alpha minus Y beta squared plus C alpha C beta squared. All right. And so if you differentiate this, the X alpha R, what survives is your X alpha minus X beta divided by the distance, which is R. Yeah. So R is this sum of squares, the square root of the sum of square roots. If you differentiate that, you have to the minus 1/2, right? So that's 1 over R. And for, if you repeat the same thing for beta, all you get is a change of sign. X beta minus X alpha divided by R. Okay. And so what you then find is that something like your sum alpha Q alpha dQ alpha E ele, right, where this is an inner product of 2 vectors, will be 1 over R times dE dr, right? And this 1 over r comes from these guys. And now in terms of Q, you still have the numerator. So you have something like this, x alpha minus x beta plus x beta minus x alpha plus y alpha minus y beta plus y beta minus y alpha plus c alpha. So this results from the inner product of your Q, so the X, Y, C, for alpha and beta with these derivatives we have above. Okay. So if you look at this bracket long enough, you will realize that this is actually nothing else than x alpha minus, you will get the same if you write out these squares. And that is the same as r squared, okay? And so the exponent 2 cancels, and you're left with r times dE dr. So this is what happens to this additional force term for your Virial theorem in internal coordinates. So the Virial theorem for any diatomic reads 2 times TL equals minus VL minus R times dE dr. And this is Ele now, right? So since your TL plus VL must still sum up to the total energy, you get TL is minus EL minus R dE dr, or VL is 2EL plus R dEL dr. Okay. So these would be the 2 expressions if you can eliminate either the kinetic or the potential energy term. Now, as discussed in the last hour, we can do the same for the total energy. So this is the electronic. For electronic energy of any diatomic, and now we can do the Varia theorem for total energy, that means including the nuclear repulsion, you have dL minus V tot minus R d R and U. Yeah. And here again, we can eliminate either, since U dL plus V dot equals U. dL minus U minus R dr U and V dot comes 2U plus R dru. Okay, so now we have our working equations, right? And we will use these in certain regimes, right? We would like to discuss now something like a binding curve. So something like this, right? And we have certain regimes which we would like to see. And this is a dissociated regime. This is a regime which is far away, right? So long range. This is the bound regime, and this is when you're nearby, short distance. And this is energy and your distance. This is U. Okay, there's some energy. This can be any unit, right? So we're going to plot also kinetic and potential energies now. But we have these four regimes we'd like to discuss now. So let's start out by considering the dissociated regime. Right. Well, what does dissociated mean? It means that we should consider the limit of R going to infinity, okay? Easy. So what happens to your total energy? Well, it simply becomes the sum over your atomic energies, right? But in the limit of infinite distance, there's no nuclear repulsion anymore, right, between the atoms. So it's simply the sum of electronic energies for each atom alpha. Right? So it's the sum of atomic solutions. And for those, we already saw the Virial Theorem in the beginning of today's lecture, right? Okay. Now, the second regime we'd like to discuss the bound case. So what happens in the bound case, right? In the bound case, by definition, du dr, where r goes to R equilibrium, must be 0. Okay. So in other words, our Virial theorem dictates that in this regime, right? So at Re, your kinetic energy is the same as the total potential energy, and it also, if we make use of above equations, we can also see that this must be the same as the equilibrium, the total equilibrium energy. And furthermore, these then result in our total potential energy at Re. So all at Re must be equals 2 times our total potential energy. Okay. Now, in the case of the distances being dissociated, right? You also have these same relationships, right? Right. Namely that du dr and r to infinity must also be 0. And then you get the same kind of relationships, only that for the last one, v dot at infinity, you have 2 times u at infinity, and this must be equals 2 times the atomic solution as discussed above. Okay, so this tells us something. These two regimes are very interesting, right? Because they consider the extreme of being as bound as strongly as possible and being as bound as weakly as possible, namely not at all. Right? So it doesn't get better than this. Right? So we'd like to know what is the difference, right? And so we can subtract them from each other. Right. So what does this result in? Then we have T, the kinetic energy at the equilibrium distance minus the kinetic energy at infinity must be equals the total energy at infinity minus your energy at the equilibrium, right? So that's the dissociation energy. Right? We also have that the total energy, the total potential at equilibrium distance minus V dot at infinity must be equal to 2 times U of Re minus U of at infinity. So by convention, this is what we define to be the dissociation energy, and we can therefore write our dissociation energy is 1/2 times the energy of V dot at infinite distance minus V at the equilibrium distance. Right. So this is a non-intuitive result that tells you that your dissociation energy has this direct relationship to the difference in potential energies. And what you also know is that this dissociation energy has to be smaller than 0 if there's supposed to be some bonding, right? And so if you know this, you basically arrive at inequalities where you can say, because of this, your potential energy at the equilibrium distance has to be smaller than the potential energy in the dissociated limit, and your kinetic energy at the equilibrium distance has to be larger than the kinetic energy at infinity. Okay. So this you can rationalize, right? The kinetic energy has something to do with the curvature of your electron density, right? And we discussed the electron density in a bond, right? It has this shape going from one nucleus to the next, right? So if you consider an electron density in a bond, right, versus 2 times something like this, right, it's clear which one has more curvature. Okay. So the left one has more curvature, and hence its kinetic energy is larger. Conversely, as your electrons start bonding to the other atom, you get more potential energy, and that's also why intuitively you would expect the potential energy to be lower, right? So this is a rigorous derivation of what you would intuitively also expect here. All right, let's now consider the case of long-range distances.
Excuse me?
Yes?
I don't understand why there is necessarily more curvature. Can you?
So the real proof is this inequality, right? The curvature argument is a rationalization of it, right? Now imagine you have two such atoms here, right? And you bring them together, right? You see that your electron density of this one atom now had to go up here to this region, right? And so this curvature versus this curvature, you would intuitively, like a hand-waving argument, you would say that this should be more curved in the bonding scenario. Does that make sense?
Yeah, well, I think it's okay. Thank you.
Thank you. All right, so let's go to the next regime. So we talked about this. We talked about the bound one, right? We subtracted. We compared these two, and now we'd like to briefly look at this long range regime. So for large R, so meaning R being with some prefactor multiple times a typical bond length, so let's say 10 angstrom. Would expect the total energy to go as your energy offset, so the sum over atomic energies minus the typical London dispersion distance relation, right? So this is strictly true for two neutral atoms of which at least one has electronic S valence. Okay, so meaning that at least one of them is spherical. For those, it's strictly true. For other atoms, this would be approximately true. But this is what you would expect. And from this, then, you would find, if you insert this again in our Virial theorems, that V becomes V infinity plus 4C 6 over R to the 6, and your kinetic energy comes T infinity minus 5 C6 over R to the 6. So we can briefly show this. T minus U minus R du dr minus U infinity plus C6 R to the 6. And now comes the fourth term. So we take R du at infinity dr. So this is 0 minus dr. Now the C6 over R to the 6th term. And that then leaves you with minus U infinity which is the same as TL at infinity, as we've shown above in the infinity regime, plus C6 R to the 6 minus R6 C6 over R to the 7. And this then means the R's cancel. And you have TL infinity minus 5 C6 over R to the 6. Similarly for V, and this is 6 times C6 to the 7. And so this is minus 2 TL infinity, which is the same as V at infinity, plus 10 6 over R to the 6 minus 6 C6 R to the 6. And so this leaves you then V infinity plus 4 C6 over R to the 6.
I'm sorry, could you repeat again where this factor comes from? This C6 over R6.
This is, I'm sorry. This is from Fritz London. Okay. So in this long-range regime for the neutral atoms, right? This is also known as London dispersion, or also van der Waals. And so from the gas law studies of van der Waals, you can arrive at this dissociative tail of R to the minus 6. But Fritz London also derived this from quantum mechanics. This is a very, the default dissociation law if in the absence of mutual polarization. So if there's no other electrostatics working, then this is the least you should expect.
In this case, what does C stand for?
The C is a coefficient, so it is related to the polarizability of your atom. And so we've discussed the polarizability before, right? So roughly speaking, the more polarizable your atom, the more the larger its C6 coefficient, right? So you can think of it as a polarizability prefactor, right? It just scales the magnitude, but the tail is dominated by this R to the minus 6. Right? Thank you for this question, right? So I sort of presumed this was known, but it's of course important to explain this. For the the short regime, we can consider so small r, right? There is something which is known as perturbation theory around the united atom. So for small r, use perturbation theory around the united atom. So that means before or when fusing the two nuclei. Okay, so now we don't talk about nuclear fusion here, of course, right? We are talking about fusing the proton charges, right? The nuclear charges, such that they add up on top of each other, right? So if you had H and F, you fuse their nuclei, then you have neon. Okay, you didn't really study the actual nuclear fusion. We don't do nuclear physics here, but we can look at the electronic Schrodinger equation for such cases. There's no problem with this, and it turns out, so one finds that the electronic energy looks as the energy of the united atom, right? So this is identical with E of an atom where the nuclear charge is the sum of nuclear charge alpha and beta plus a quadratic term plus a cubic term plus a quartic term So this is roughly how it looks like. And you can show, and we don't do this here at the moment, not shown here, that this leads to V corresponding to Z alpha times Z beta divided by the distance plus V L at R equals 0 plus 4AR squared. So this term here basically makes or turns this into a minimum. Right? This corresponds to a minimum. Right? There's a parabola in the distance, and right, but this term here diverges, and that divergence will take over, right? So this minimum does not survive, but for the kinetic energy, turns out that you have the L of R equals 0. That is not divergent, and you add to this a flipped parabola. So this is a maximum. Okay. All right. So now we discussed these regimes, and we can now use these regimes to make a drawing of a bond. And I'd like to very quickly, we are running out of time, but I'd just like to give you, we will discuss this in more detail tomorrow. We will finish this discussion, So if this is your binding curve, right? Sorry. Then this is your sum over your free atoms, right? This would be your energy 0, and this is your curve U, right? The total energy. And then we will find that we have this offset here, and this is the dissociation energy. And then what we find is offset in this direction. And again, with the dissociation energy, the kinetic energy will look something like this. While the potential energy goes way down here with 2dE, and it will look something like this. So this is V and this is T. All right, we will discuss this in more detail, this picture, tomorrow. I'd like to thank you for your attention, and I wish you still a good day, and see you tomorrow. Bye-bye.